Our next presentation is going to be from the esteemed Andy Rayner, CTO of Nevion, now a unit of Sony. And he's going to be talking about some real life work that he's done with 5G networking for live production. And this is really some interesting stuff, so we're very much looking forward to it. Take it away, Andy.
Thank you, sir. It's good to be with you again. This is my last stint for NAB 2022 on this booth, so thanks for joining up. And if you're watching again online, it's good to see you wherever you are. Okay, before I launch into the detail of 5G, I just want to give the context in a couple of slides as to where we're heading as an industry. Two key things our content producer customers are looking to do. One is to up production value, and the other one is to reduce cost. But to actually achieve both of those things, what they're really looking for is flexibility. And what we're going to be talking about in 5G really actually plays into that, because 5G potentially, with what we're able to do, gives us immense additional flexibility. So this is my go-to picture. I've actually used it on every presentation, and I don't apologize for doing so, because it actually shows the whole ecosystem of what we're actually looking to do with live production moving forwards. It shows all of the different components, both those for cloud infrastructure, for storage and processing, central facility infrastructure, remote facility infrastructure, true at-home, as in domestic home, remote panel control, but also, very importantly and relevant to this conversation, on the top left, 5G infrastructure, which actually allows us to do those very agile connectivity for acquisition and control. And this actually belies the advantage we're actually giving in terms of, or the true advantage we're gaining from IP infrastructure. When we actually relate that with the 5G elements we're talking about today, we can share people resources, equipment resources, and real estate very dynamically from multiple locations. Okay, so that's the context. Now getting into the 5G element of what we're talking about. 5G has immense potential for broadcast in several ways. I'm going to be focusing very specifically on the right-hand side there, looking at mobile production, so mobile live production, and that's the work that we've been looking at, and some of the actual real-world trialing and testing that we've been talking about. So, deployment prioritization for 5G. Pretty well everything that you're experiencing, if you've got 5G on your phone, is what we call enhanced mobile broadband. It's basically more of what you got with 4G, but better in terms of its lower latency, and it's much faster. There are, however, several tenets of 5G that have different capabilities, which are in the 5G toolkit, if you like, which actually are enabling other things. One is the ultra-low latency, high availability. Some of those words may ring true to what we do in broadcast, but that is typically from the mass market being targeted at automatic driving, so automotive interconnecting signaling between cars that are automatically driving. There's NIoT, the Internet of Things. These typically are things that there are many millions of them, tens of millions per square kilometer or whatever, but they require usually very tiny amounts of data, and want typically good battery life as well. So that's not a relevant topic to where we're looking at, but it is an important use of 5G. And then where we get to at the bottom is the custom QoS slicing. So there is the potential within the 5G toolkit for us to actually have the ability to customize and have guaranteed performance within a slice of a 5G infrastructure. And that's when it becomes very exciting for broadcast, because we want that deterministic performance. A couple of other definitions or for you within the 5G elements that we're talking about, because you'll have heard possibly about these two different scenarios in different ways. 5G is a radio toolkit that can be applied in different ways. On the right-hand side there, you'll see mobile network operator. So that's the guys that are doing the 5G services to most people's phones. And we call that an MNO service. And those are being provided, and at the moment, as I alluded to previously, pretty well is just providing enhanced mobile broadband. However, there is the use of 5G as a radio technology to actually run non-public networks. So if you get the licensing for the wavebands, then people can actually put up their own private networks, which allow them to actually make use of the full capability and the full toolkit of 5G, but not part of a mobile network operator infrastructure. And both of these plays have actually important applications in live production. The left-hand one here, it actually provides a toolkit to provide very high bandwidth within, say, a stadium environment where you can actually do a completely wireless infrastructure for everything. If we're looking at for what a lot of broadcasters are looking at for what I call pop-up production, where maybe you want to bring 1, 2, 3, or 4 cameras that you actually want to literally come up anywhere in the country, rock up, turn your cameras on, and you're on air within 1 minute, then it's the MNO infrastructure. And there are different capabilities and different restrictions which we're going to unpack there. This is probably a complex slide. I don't need to actually talk too much there, but it's the bit on the right, the slicing, the network slicing that actually potentially allows us to have the best of both of those worlds. So like that private performance on an MNO network. That is, however, dependent on the mobile network operators actually offering what is needed in terms of the commercial offering that realizes those capabilities. So Nevion's been involved in a few different pilots and testing work in recent times, and I'm going to specifically unpack most for the next few minutes Virtuosa, which is a project we've been heading up that's been Europe-based. But these are key trials which have allowed us to actually really push to the limits and evaluate if you like, the native performance of 5G infrastructure and what it's capable of. This is my go-to overall picture of what we were looking to achieve within these infrastructure, and this gives you some concept. So you've got what I call the 5G cloud there, if you like, in the middle. There are two key things we're interested in: is peering with the data infrastructure, so the data flows, the media data flows to and from the cameras and monitors and control surfaces, whatever we're trying to actually have in 5G. You've got then your acquisition devices here on the left, the cameras and the microphones, etc. And then potentially the other connected devices, which may be remote control surfaces. People have talked about people doing a TD function from the corner of Starbucks by having a couple of nice interactive screens with a decent mosaic of all your video feeds and being able to make those decisions. Those kind of things are potentially possible with the toolkit that we have available to us. So just jumping through to the actual Virtuosa specific project I'd like to just tell you about for a few minutes. These were the parties that were involved. Nevion was heading it up, and I was significantly involved in overseeing that. We also had some significant supporting friends on the right-hand side who were able to actually contribute and actually provide capabilities for us. I'm just going to show you a few videos while I talk about the project here. So this specifically it was a multi-location environment that we did testing, and we managed to do testing in the UK and in Germany. So this is actually arguably one of the homes of radio. This site in Germany has been doing radio since 1906. And this was one of the locations we chose because there was an existing 5G cell infrastructure there that enabled us to do some testing. We actually set up a lot of equipment. There was some indoor as well as outdoor 5G antennas in this location, so we were able to make good use of that. So this is the location where I'm based in the UK, Adastral Park. We actually did some testing. There, again, very fortunately, we've actually got 3 5G cells set up for test networks on site. So we were able to do lots of testing. And in fact, we did the final test we did on the very final day, which is what you're seeing the video of here, was actually, no, it's not here because this was me. We actually did some testing where we actually had live feeds coming internationally from the UK into Germany as part of the infrastructure. And finally, I think this is the final location. This is ARD. It's a broadcaster down in Frankfurt in Germany. And what we were doing is we were long lining both of those 5G infrastructures from Nauen in Germany and Adastral Park in the UK down into ARD, where we were actually pulling those in together with a whole load of other infrastructure and feeds that were generated by this broadcaster. And then we were long lining that infrastructure back and doing remote production from that end, which is about maybe 400 kilometers away from this site. So let me just whistle through what we've been looking at in the environment in the Virtuoso project. First of all, very briefly, we did a traditional, I say traditional, sounds strange, IP LAN production where we had infrastructure, where we actually had a local area, a classic local area IP production network. We then actually long lined and actually started to look at remote production by having multiple locations. We actually had 3 different locations where we actually were able to actually interconnect with independent management and actually do a traditional fiber connected remote production. And then we actually went to the bit that I just showed you some video clips of, where we actually had that remote location connected by fiber. We had 2 locations connected by 5G infrastructure. I've got a tiny diagram here, so you're not going to be able to see this very well, but I can show it to you later if you like. But it just shows you the interconnect that we had in the UK, in Nevion in Germany, then down in Frankfurt in Germany, and also some cloud connectivity to complement, which I'm not going to go into. If you want to look at my video on cloud connectivity from the other day, then please check that out as well. So this was fundamentally the setup that we had. I just want to spend 2 or 3 minutes now unpacking, just looking at my time budget, unpacking some of the technology. Okay, so first of all, let's dive into some of the deep tech on the packet structure of 5G. One thing it's worth pointing out that in a traditional MNO 5G deployment, such as we are all receiving on our phones, one of the things about that is we need, by design, there is a heavy downlink asymmetry, because most people want to pull a lot of content, and most people are just sending a few secure HTTPS requests northbound. If you can think about the application we've got for broadcast, if I am a camera, a broadcast camera, then actually I need the reverse of that. Most of my bandwidth is needed uplink centric. I don't know if you can see here, but this is a typical configuration of a 5G cell here. And what we have is a very heavy downlink performance, the green there compared with the yellow. So that shows you the typical way a 5G infrastructure is set up. So we have a heavy asymmetry. Now, it just needs to say that doesn't need to be the case. The asymmetry is by design and is fully configurable. So if you actually have a private slice on a 5G cell, or you have an NPN, a non-public network cell that's under your full control, you can actually define that characteristic of uplink versus downlink entirely under your control. So it's only if we're actually trying to sit in with an existing MNO infrastructure that's not giving us guaranteed slicing that we actually have those challenges. Anyway, just wanted to point that out, but that shows you the typical configuration we have at a low level on a cell. I'm not expecting you to read this, but I just want to talk you through it. This is showing you the testing we did on a traditionally configured cell in terms of the bandwidth, uplink and downlink, and the important figures are the ones bottom right. So if you see here, the aggregate cell uplink bandwidth we have in this particular scenario with that heavy asymmetry is 124 megabits per second as a possible uplink capacity on this cell. And if you look down there, you've got roughly 1.5 gigabits per second on the downlink. So that gives you some idea of the available capacity if we were to reconfigure the cell and change that asymmetry. But it does mean even on a classic MNO configured cell with a heavy asymmetry, we've still got 120 megabits per second available as uplink that we can make use of for the connectivity. So one key thing is bandwidth, the available bandwidth. So this gives you some idea. It's also worth saying that there are 2 different frequency spectrums that typically 5G is running in. Most of what you'll be experiencing, in fact, pretty well everything you'll be experiencing is sub-6 on your traditional EMBB MNO cell. Typically 3.8, 3.7 gigs is the spectrum that's being used there. There is, however, millimeter wave, which is up 27 gigs and beyond. And that actually has because it's much higher bandwidth, there's the potential to actually have much more aggregated bandwidth available there. But typically that's not being used for MNO, but that's the technology spectrum that you can potentially use for private 5G infrastructure. Another key thing is latency. Latency obviously is vitally important for us in broadcast, especially in that acquisition phase at the front end. And this shows you, I'll just talk to you, but the bottom of these graphs here is typically we're seeing is between 20, 25, maybe drifting on some infrastructure up to 30 milliseconds. So that gives you an idea of the latency that's incurred in that transport, in the transport of the packets. And that's to do with the way the handshaking works, the data requesting and the buffering that exists in 5G infrastructure. So roughly speaking, you've got somewhere in the order of 1 video frames latency that's you're losing just because of the 5G infrastructure and the way that actually works. So just jumping into how some of the tests we did at the media layer now, rather than the 5G data transport layer. First of all, we did actually UHD and HD testing here. We were very privileged to be able to use some prototypes that Sony lent us of some ultra-low latency compression, which you can actually check out on the Sony stand, if you like, in the far corner of the Sony stand. And this is HEVC with a end-to-end latency encode to decode of sub 35 milliseconds, which actually really plays in well, and I'll show you some of the end-to-end latency results that we had on this. But we were using this, but typically what we were running UHD at maybe 80 megabits per second and HD at somewhere between 25 and 35 megabits per second. So those are the kind of data rates that we were actually using there. We were actually able to make sure that we actually did multiple streams on a single cell to actually check performance and the bandwidth sharing that happened between those as we go. End-to-end latency, so this is basically what I was just telling you. We actually did some what I call baseband video tests. We broke it back down from IP to into SDI just to do a traditional video. And you can see once we've got the measurement we were taking in the baseband SDI encode to decode was 38 milliseconds there. So that gives you an idea of the performance looking at there. I'll jump through that. Also worth saying, the final latency tests we did were glass to glass, because it's very important to actually make sure we actually encountered the whole system. And what I was just going to show you is there's a very handy app that we were using, which was NTP locked, and we actually made sure in each location in different countries, in Germany and the UK, we actually had the same lock. So we were using this application, which is a 60 frames a second. Not 59.94, but that enabled us to actually verify the latencies that we were measuring electronically in different layers, actually glass to glass, even between countries, to actually make sure we pulled those in. So that was very useful. So here is some key numbers just to show you the kind of latencies that we were looking at. So on the local tests that we were doing, the local infrastructure without long hauling connectivity internationally, we were able to achieve 60 milliseconds as the latency from effectively the latency from the camera acquisition to the use point in the production. And when we were doing international connectivity, so this was actually going between the UK and Germany as part of that infrastructure, we were actually achieving 140 milliseconds. And that, I just like to throw in, the reason it was 140 milliseconds is we were allowing for a round-trip ARQ technology to protect the international connectivity as well. So in both of these scenarios, we were using ARQ protection as part of the toolkit to protect the 5G infrastructure. But when we were actually running it internationally, we were extending the ARQ technology to wrap around the international as well. So that, arguably, some elements of that could be reduced if you weren't using the ARQ technology in the long line. If you want me to unpack any of this after the session, I can hang around for a few minutes to actually talk to you. Just wanted to point out, we also did verify the audio, and we were looking at lip sync through the system as well as actually making sure that the audio elements were covered as well. So I've talked largely mainly about what I call the data plane, the media data plane, getting the video and audio through the system. There are a couple of other issues that we need to address, when we're doing contribution. If we want to do what I make it truly part of a typical contribution production system. One is, in many cases, letting a camera free run and actually synchronizing that in downstream is actually a fine thing to do. So in which case we're not worried about synchronizing the cameras. However, there are some applications, especially if we're inputting into VR or AR systems, or we're actually doing very, very frame accurate work between multiple cameras, then we actually want the effectively to do a gen lock of the cameras, an RF gen lock of the cameras, to actually get them aligned in terms of their scans. So there are technologies. You'll be aware in 2110 we actually use PTP and we use RTP timestamping, but there are timing technologies within 5G that we can actually extract to make use of very accurate timing to allow us to actually do that SMPTE 2059 epoch derive starter frame using absolute time. Sorry, my watch is talking to me. Siri is trying to talk to me. So we can actually derive timing from the 5G native timing infrastructure. This is some work that's still ongoing, so this is not complete yet, but we're in the throes of looking at this to actually be able to do SMPTE 2059 epoch timing to do the equivalent of what we would do with PTP in a wired world, in the traditional fiber or wired world. Also, orchestration is another key thing, because what we really want it to end up with here is the control plane being integrated as well. So if we are actually wanting to request from the 5G infrastructure specific performance, specific slicing parameters to give us the QoS, give us the required bandwidth, then our traditional orchestration tools, which we have honed lovingly to work in a terrestrial fiber connected world, and we're using all the time in IP production infrastructure, we want that to engage in the 5G network as well. So one of the other things that's work in progress still is to look at how we actually make use of the fairly rich API that's defined in 3GPP for 5G, and actually make use of that to actually dynamically control, so we can actually create true end-to-end workflows that are connected using the 5G infrastructure as well. Okay, so that's a little bit of overview of some of the technologies. We've actually worked with our partners in Germany. They've been looking at some use cases in Germany. We've also, some of our friends in Sony, and just pre-pandemic, had done a couple of useful trials in the US and in Germany as well. So coming back to my generic picture of like live production moving forwards, we believe that the potential of 5G to actually provide agile and cost-effective elements to complement and be part of a holistic, dynamic and distributed IP production is immense. There's immense potential there. The way we actually use 5G is going to be different in different ways. So some of it may be using mobile network operator infrastructure with or without slicing. And some of it may be using NPNs, non-public networks, where we actually can potentially exploit the millimeter wave band rather than sub-6. And we can also potentially then change those asymmetries and get significantly more bandwidths available to us. Okay, hopefully that's given you a whistle-stop tour of what we've achieved, what the potential is. If you'd like to unpack that or reach out to me, I would love to actually talk to you further. For most of when I'm not around elsewhere, I'm going to be on the Sony booth later on. Do come and find me, or do reach out to me on my mobile or my cell number there. I'd love to talk to you. And if you're ever in the UK, I don't have a kettle with me at the moment, so I can't make you a nice cup of tea here today. But if you're ever going to be in the UK or catch me at some other point, I'd like to make you a nice cup of tea. Thank you very much. I think there is time potentially for a few questions.
Thanks for that, and we have time for some questions. We'd like you to be on the mic for that, so here you go.
Andy, a great presentation. Something that I didn't understand. You said that some of the content was 80 megabits, right? But the 5G that you showed could only handle like 40 megabits. So did you bond that, or how do you overcome that problem?
Great question. So the actual figures on the MNO network that I showed you with the asymmetry, we had an uplink capability of about it maxed out at 125 megabits per second. So we were actually using between 75 and 80 for a single UHD stream. So we didn't need to bond because that was a thing. We had 120 megs available uplink, which was usable within the infrastructure. So we typically were using for a UHD stream 80 megabits per second on that.
Now a question about the ARQ. I'm guessing they did only one round trip. So how good was it? How many errors did you see on that link?
Another good question, and I would expect that question coming from you, sir. Basically, on one of the two networks, and I'm not going to reveal manufacturers or locations, one of the two networks, we actually found that in the local environment, the packet loss was negligible. So ARQ was actually not necessary, even though we had it running. It's worth saying that the way the 5G cells typically negotiate is they actually kind of work with a certain packet loss target. So they are actually assuming, in a fiber world, we use a term like quasi-error free. So you're expecting pretty well perfect connectivity. Typically, the way a 5G infrastructure works is it negotiates to a point where it gives you a certain bandwidth, but with a certain cell loss ratio, and therefore my expectation is with most of this connectivity, you're going to need to employ ARQ to guarantee. Or FEC. I mean, you could use FEC. I mean, the challenge, as you're aware, if you use ARQ, then you've actually inherently got a loop's worth of latency that you've got to have to allow you to do retransmission. So there's a combination. There are other things that you can do within a 5G world, because especially if you're in a dynamic situation where you're moving with respect to the cell, then your channel bandwidth is going to vary. So there are some of the techniques certainly that Sony have been looking at as part of the toolkit is adaptive bitrate as well. So the actual encoder will slew the bitrate to actually allow you to maximize performance within the available channel. But obviously that has to be negotiated carefully if you're in a multi-camera environment where you've got several cameras uplinking to the same cell trying to actually use shared bandwidth. So one of the other tools we're looking at in the orchestration domain is actually the orchestration system dynamically brokering the available bandwidth to the available clients on a cell to make sure we can actually optimize and give guaranteed data flows.
All right, so thank you very much.